this set up. So the diagram that you've seen before that you're going to see today is when you have a triangle within another triangle like this one. And in this diagram, actually XY is called a mid-segment of the triangle. It's kind of like the mid-segment in a trapezoid. So it's a segment that connects the midpoints of two sides of a triangle. So it says there XY is the mid-segment of triangle RST, so of the large triangle that you see, and that means X would be the midpoint of the side RT, so XT and RX would be congruent segments, so XT would equal RX, or you could call that XR, and then that means Y is the midpoint of the side TS, so TY, and then YS or SY would be equal as well. So not necessarily all four of those segments congruent to each other, but you do know that X is the midpoint of RT and Y is the midpoint of TS. But then it does ask how many mid-segments will every triangle have? Any ideas? Every triangle has more than one mid-segment. So, Hunter? Would have more than two. It would have three. So we have three sides of a triangle. All three sides have a midpoint. So it's not drawn in, but I could draw a midpoint on side RS. And that means I could also connect, like let's say I call this Z. It doesn't really matter in this case. But that means XZ, if I drew in XZ, that would also be a mid-segment because it connects two midpoints. And then ZY would be another mid-segment. So every triangle does have three mid-segments because each of the three sides has a midpoint. So XY would just be one mid-segment. But then that brings us to the triangle mid-segment theorem, and it states that a mid-segment is parallel to the third side and is half its length. So that's probably, yes, being parallel is key, but knowing that it's half its length is also key. So in this triangle, I know I just drew in two other mid-segments there, but that means XY would be parallel to RS. And those are the pictures like you've seen before, where you have a triangle with another triangle, and you know that two of the sides are parallel to each other. So XY and RS would be parallel, and that means XY would equal half of RS. Or you can calculate that as RS divided by 2. And that's specifically if you know XY is a mid-segment. So that's why it's the mid-segment theorem. So in these three examples, it says, or it tells you that JH is a mid-segment of triangle KLM, and it says to find the value of X. So in example 1, if JH is the mid-segment, that means it's parallel to LM, and it also means that it's half of its length. So if LM is 30, JH would be 15. So I'm going to write this here just if you want to include it in your notes to know how you're getting that. It'd be equal to 30 divided by 2, so it would be 15. Okay, so if you know it's a mid-segment, that's how you can find, or an easier way to find those missing lengths. So like in example 2, again, we know JH is the mid-segment, so it's parallel to LM. And we are given JH is 9, so what would LM be? It would be 18. So JH is half of LM. So in this case, to find X, you would multiply the 9 by 2, and that would be 18. And I realized this after it was copied. This didn't do a great job of explaining this in the directions up here. So this is assumed this drawn in here. Actually, it was drawn in on all of them. That this segment is also a mid segment. So whatever point it's going to here would also be a midpoint. So in example 3, if this is 8, then we know this is 8 as well. So what does that make x equal to? 8, yeah. So that total side would be 16, half of that is 8. So that's the triangle mid-segment theorem. Questions on that? Okay, so then we get to the triangle proportionality theorem, and this is what I know some of you have already been using this because you realized that it worked, and it's fine if you had been using it already. Triangle proportionality theorem. So this is in any triangle. So this is not just if you have a mid-segment. So I know this picture is the same as what we saw above. So XY here does not have to be a mid-segment. In any triangle, a line that is parallel to one side of a triangle separates the other two sides proportionally, and the converse is also true. So what this means is if I know that XY is parallel to RS, then I know that these sides, where the x and the y are, they are splitting these two sides proportionally. So I know that xt is proportional to yt. And then I also know rx is proportional to sy. So they're not congruent, they're proportional. So xt is proportional to yt, rx is proportional to sy. And then there is another way. So this actually shows a different way to write that. So you can set up, and some of you maybe have noticed this already, there's different ways to set up this proportion. I know I just did xt over yt, rx over sy, but I could also write this as, like it's written here, I could write rx over xt, and then sy over yt. So as long as when you're setting up that proportion that you're keeping the ratios lined up that way, and if you, while you work through examples, it's kind of, I don't know, can be more confusing to explain. But if you are setting up examples, just let me know if you're having trouble setting up those proportions. But that's what it says here. Then if you know, this is what it, when it says the converse is also true, the converse is if you reverse that statement. So if I know that these two sides are split proportionally, then I can make the conclusion that xy and rs would be parallel. So it's just kind of flipping what you know and what you're concluding. And then what these three lines down here are for. This is just looking at if you have three parallel lines, looking at proportionality with parallel lines specifically. So I'm just going to write here, we're looking at proportional parts of parallel lines. Okay, so if you would like to, this actually comes from the triangle proportionality theorem, why this is true, and I'll explain that. But if you have 3 or more parallel lines, and you have 2 transversals cutting through them. So say I have one transversal here, another transversal over here. And then I'm going to label these as points. I'm labeling points, not angles. But I'm going to label these 3 points here, A, B, and C. And then I'll label this D, E, and F. Okay, so the proportional parts of parallel lines, what it says is if I know these three lines are parallel, so if I can call this line AD, so if line AD or segment AD is parallel to segment BE, which is parallel to segment CF, then I know that it splits, that transversal splits into proportional parts. So I know that AB and DE are proportional and BC and EF are proportional. So I can say AB over BC should be equal to, that ratio would be equal to DE over EF. And of course I could write that, other ways. I could say AB over DE equals BC over EF. There's different ways to set that up, but it splits it proportionally so that those ratios would be the same. And that comes from the triangle proportionality theorem, because if you extend these transversals long enough, you could see how it would create a triangle, and then you would have proportional parts of a triangle. So it does stem from that. But you will see problems that just have parallel lines and not triangles in them today. And then the converse of the triangle proportionality theorem, this is just in words on the back. We already talked about it, but that said, if a line is separating two sides of a triangle proportionally, then it's parallel to the third side. So that is exactly what this is stating here. Okay, so I probably should have moved that to be on the same side, but that is what we had just talked about. So looking at some examples. So example 1, you have seen examples like this before. We set them up differently. Some of you realized you could set it up the way I'm going to show you today, but otherwise we set them up differently before. So it says in triangle ABC, EF is parallel to CB, and it wants us to find X. So before, you may remember the way we set this up is I had to say, well, 18 would be proportional to this entire side. So I did 18 over this entire side by adding these together. And then I did AF, so the X plus 22 over this entire side by adding these together. And you can still do it that way, but this is what that triangle proportionality theorem states. It says I can set it up this way instead. I can say 18 over 6 should be equal to X plus 22 over X plus 2. So these parts are proportional to each other. So it makes it a little easier to set up. Some of you I know had already kind of realized this before. So now I would solve this proportion. So find my cross product, set them equal, and be careful about the distributing. So I would have 6 times the quantity, X plus 22, and that would equal 18 times the quantity, X plus 2. So I have to distribute the 6 and distribute the 18. So I would get 6x plus 22 times 6, 132, would equal 18x plus 18 times 2 is 36. And we are just trying to find x. So I'll subtract 6x from each side. So 132 is equal to 12x plus 36. Subtract 36. And that would give me 96 is equal to 12x. Divide by 12. So my answer up here, 96 divided by 12 is 8. Okay, so this is a second way to set up problems, which might be a little bit easier to set up than we did before. And you can only set it up that way segments are parallel to each other. That's the only way this works out. Questions there? Okay. So then in example 2, it says in triangle GHJ, so the full triangle, it gives us HK is 5, so I'm going to label that on here. KG is 10, and then it says JL is half the length of LG. And it is asking, is HJ parallel to KL? So it wants to know if these two segments are parallel to each other. So what I would look at is, we know that if the ratio between these two segments is equal to the ratio between these two segments, then we know that these two segments would be parallel. So let's say I call JL, I'm going to call that X. If I know JL is half the length of LG, that would make LG twice as long, so 2x. Okay, so if I set up my ratios, I know HK over KG is 5 over 10, which is 1/2. And then if I do JL over LG, the way I have it labeled, I have X over 2x. And in this case, this is like 1x on the top. The x's can cancel out, and I can see that ratio is 1/2. So because they are proportional, I can say HJ and KL are parallel. So for this type of problem, this is what you need to show, that you need to show that these two ratios are equal. It's kind of like proving triangles are similar. Here you're proving two lines are parallel. So I can say, yes, HJ is parallel to KL since, and I'm going to put HK over KG is equal to JL over LG. So even though I don't have a specific measure for these two segments, based on how I labeled it with a variable, I can see that no matter what X is, that ratio is always going to be 1/2. So that's what that is looking for, making sure that you're finding the ratios and that they are equal to each other to show that the lines are parallel. Questions on that one? Okay. Then the third example there is not dealing with a triangle specifically. So this is dealing with proportional parts of parallel lines. You can see that these three segments do have that parallel symbol. They're all parallel to each other. So it says frontage is the measurement of a property's boundary that can run along the side of a street, lake, ocean, or river. It says find the ocean frontage for lot A. So we are looking for this length right there. I can call that X or whatever you want to call it. So because I know these three segments are parallel to each other, I can set up a proportion with these parts here. So I can say X over 60 should equal 58 over 42. That's one way to write the proportion. You could write it differently. There's, like I said, there's equivalent ways to write that are fine. But then however you write your proportion, solve it. I should specify there is a wrong way to write a proportion as well. So as you're working through these, if you're not getting the right answers, just double check that you're writing your proportions correctly. So here I would have 42x would equal 60 times 58. So 3,480. And then if I divide by 42, then x would equal getting a decimal, so I'm going to round it to at least one decimal place. I got 82.857 and so on, so I would call that 82.9. And it was giving me yards in the problem as a unit, so I'll put yards after it. All right, so some of these remaining examples I am going to have you work through on your own or in your groups, but there are two that I would like to do together, and then I'll kind of let you know which ones I'd like you to try so that we can check things off here. So for sure, we're going to go through this example 5 and 7 together because we haven't been through an example like those just yet. So in example 5, so this kind of goes along with the mid-segment theorem for a triangle. So we have three congruent segments, or three parallel segments, three congruent segments. So because these are parallel, if you know that all three of these segments are congruent, then you can conclude that all three of these segments are also congruent. So I know that 12 is congruent to 2x minus 6, which is congruent to x plus 3. So if I'm looking for x in this problem, I just have to set two of those expressions equal to each other to solve for x. And you can pick which two. I would probably set, to me, the easiest would be setting x plus 3 equal to 12. And then solve for x, so I would subtract 3, and then I know x is 9. And you could then double check. So if I substitute 9 in to these two to know that I should get 12. So here I know I'm going to get 12, 9 plus 3 is 12. And then here 2 times 9 is 18, and 18 minus 6 is 12. So you can make that conclusion if you have parallel lines and they're splitting one side into congruent pieces, the other side must also be split into congruent pieces. Okay, so that can be helpful to know that to find missing variables. And then 7, I wanted to go through also just because of how the answer works out. So for this one, I don't know that anything is congruent. I do know that these three lines are parallel to each other, and that must mean that it splits the other two lines into proportional parts. So I can set up a proportion. I can say 5x over 3x should equal, and then it would be x plus 12 over 12. Now, you certainly could leave it like this and go through and multiply your cross products to try to find x that way, but you'll end up with an equation that would require factoring to solve. You can get away in this one, you can get away without factoring if you realize that in this ratio right here, I can simplify the fraction first by canceling out that x. Okay, so 5x over 3x is equivalent to just 5 over 3. Kind of like dividing both numbers by 2. Here you're dividing them both by x. So I would have 5 over 3 is equal to x plus 12 over 12. And now I can solve for x. So if I multiply my cross products, set them equal. So I would have 3 times the quantity x plus 12 equals 5 times 12, which is 60. And then I can distribute the 3. So 3x plus 36 equals 60. I'll subtract the 36. The 3x would equal 24. And then divide by 3. and I would get x equals 8. So that would be the value of x I'd be looking for, the non-zero value of x. If you did do the factoring route, if you would have left the x here, and I'm not going to give you a problem that's going to try to trick you, but if you had left that there, you'd get a second solution of 0, which 0 in this case for x wouldn't really make sense because both of these lengths then would be 0. So 8 would be really the value I'd be looking for, and you can get that by canceling those x's out. Okay, so for the examples I'd like you to try, actually, these three should go fairly quickly. So the 5 remaining, so 1, 2, and 3, and then 4 and 5. Just take a few minutes to work through those. Some of you might have been working ahead and worked through some of them already. And then I'll walk around, answer questions, check what you have, pass out the assignment. The remaining time is for you to work. And let me know if you have questions on anything. Homework.